twice. I'm Pitoura, and I'm going to talk, and I'm very pleased because I'm going to talk about a very important topic, fairness in AI. And today we are going to address three important questions. Why fairness in AI, right? Can an AI algorithm be unfair? Spoiler alert, yes. What is the cause of unfairness? And the short answer is biases, and I'm going to elaborate on it further a little bit later. And then how can we mitigate unfairness, right? So I'm a computer scientist, so I'm going to give you a very short overview, high-level overview of the way we've been trying to model unfairness, and also how we are trying to mitigate unfairness in AI algorithms. Okay, so I guess this is an interdisciplinary audience. So how many of you are computer scientists? From the lawyers, or okay. And from the medical domain? Okay, so we have people from various domains, which is great. So I'm going to keep my talk in a high level, so everybody understands something, and hopefully everybody learns something out of it, right? So let's start by question number one. Can an AI algorithm be unfair? Okay, so I don't have to motivate AI. You always, every day you hear about AI. There is this hype of AI, and of course, there are enormous opportunities. For me, one of the most important ones is scientific discovery. We expect a variety of new results in many domains, in the medical domain, from the medical domain to astronomy, right? And then it promises to improve the quality of life. We have extremely new important results in areas like NLP, speech, vision. Okay, but with great opportunities come great responsibility. And so we live in a world where decisions are assisted or even taken by what I will call AI algorithms collectively. I mean AI systems, models, and so on. And remember, these AI algorithms are black boxes, right? You have heard it many times. Means that we are not completely sure why we get the output we get. And also keep in mind that all these algorithms are trained, learn for an enormous amount of data. Okay? And we use them, as I said, to help us, assist us in taking decisions. And this includes personal ones, simple personal ones, simple decisions like, well, what movie to watch. More important with decisions like what job to take, or what university to attend, right? And also, most people get informed, learn the news from social media. Okay. So recommendation algorithms behind the social media, TikTok, for example, determine which news you will hear, which stories you will learn about. So in a sense, they take a huge part in forming our opinions and our own view of the world. And this is not just personal decisions taken by individuals. This includes decisions taken by organizations, public and private organizations, in healthcare, in insurance, in housing, in education, in school admission, in law, in courts, in job recruitment, okay. And of course in medicine. AI is used in prognostic, in diagnostic, in therapy, to recommend treatment, to allocate benefit and resources in precision medicine. And this raises concerns regarding how much can or should we trust AI systems. And such concerns are not without a reason. We have many findings that show that human biases are introduced and are sometimes exaggerated through these AI algorithms. So in the next few slides, I'm going to present 6 examples where AI algorithms were shown to be unfair. just to give you an idea of the types of unfairness that we can experience in such systems. Okay. My first example is a very well-known example, is the combat system. It's an example very, very often used, and there are a lot of papers written on this system. How many of you have heard about the combat system? Okay, so a few. It's a system that is used in the US court for bail and for helping judges in bail and sentencing decisions. It's a commercial tool that predicts the risk of reoffending for specific categories of future crime. Okay. And in an article a few years ago, it was shown that it labeled as higher risk people from African Americans that did not reoffend. This percentage was double of the percentage of white people. That was a false positive, right? And then it labeled lower risk people that didn't reoffend. The percentage here was double for whites than African Americans. Okay. And why? Because this system was trained on historical data. Another example comes from the area of water beddings. Have you heard about water beddings? Okay. How many of you? Okay, larger audience. What are water beddings? There are in many large language models. What we do is that we represent words as sequence of numbers, as vectors. For example, banana, it's a example, can be a vector that you see there. And how do we get these vectors? What we want to do is to get words that appear in similar contexts to have similar representations, similar vectors. Okay? So this example is from beddings trained on a corpus of Google News text, and it was shown that these beddings reflect gender stereotypes when it comes to professions. And there is a paper that with a very nice title, which says, "Man is to computer programmer as woman is to homemaker." This is called analogies, and what it means is the following. It's kind of impressive. If you take the vector representation of man and the vector representation of women, and you subtract them, okay, and then you take the vector representation of computer programmer and the homemaker, and you subtract them, the vector that you get are very similar, right? This is called an analogy, and it reflects a stereotype, right? This is not surprising in the sense that you are expecting something like that, right? Because it's in the text. However, and the problem is that these embeddings are used as input in many ML algorithms. They are used as input in systems that are used in hiring decisions. Okay, and you train the systems saying that a woman is better as a homemaker. Right? And I have a few more examples just to show you the different cases. Another example is from Google search, Google image search. So you search for doctor, and you search for nurse, right? What kind of images you get? What is the percentage of images portraying women in image search for professions? And it was shown, this is a kind of older study, but it shows that there is evidence for stereotype exaggeration, meaning that there was systemic underrepresentation of women. That is, the images of women shown for specific professions were smaller than their actual percentage as estimated by the US Bureau of Labor and Statistics. My fourth example is from the Dutch Tax Authority for risk assessment that used an AI algorithm to determine child care benefits fraud. And it was shown that dual nationality and low income was a factor in this system. and it resulted in a fine. And a very known example is also from Amazon recruitment. A few years ago, 10 years ago, less, it was shown that the AI algorithm that Amazon used in recruitment was biased against a woman. And the reason was that it was trained mainly on male TVs because they have more candidates that were men. And my last example is from, it's quite recent, is from the healthcare, a healthcare risk assessment tool that is used in more than 200 million people in the US to determine which patients should get high-risk care management. It was shown that white patients were favored over African Americans without race being a factor in that system. Okay. But the system used healthcare cost history, and black patients include lower healthcare costs than white patients with the same conditions. And finally, what happened was that those that did get high-risk care management, the black individuals among this group have 26.3% that more chronic illness than the white ones. Okay, so you have seen a range of case studies, a range of examples where a fairness or an AI algorithm was unfair for various reasons. Okay, so let's now discuss and think a little bit about what is the cause of unfairness. So question number 2, what is the cause of unfairness? And as I said, the short answer is biases. Now, bias is an overloaded term that is used to capture various forms of misusing data and information, prejudice, behavior, and favoritism. And I copied here a definition from Oxford English Dictionary, which I found interesting. It's an inclination or prejudice for or against one person or group, especially in a way considered to be unfair. There are many, many different biases and various categorizations of biases. I will consider and talk about 2 types, societal and statistical biases. So let's start with statistical biases. Statistical biases or sampling biases happens when the data set selected as input to an algorithm is not representative of the whole population to which the algorithm will be applied. Okay. And there is also the term, you will also see the term selected labels in this general type of statistical biases, which means that the observed output depends on the choice of input. For example, in courts, the outcome of whether a defendant fails to return for court is observed only for defendants that are released on bail. So there are sub-types of biases like this. Sometimes we also use the term selected bias to refer to non-random selection of input. And I have some example for statistical bias from the medical domain. It's from a paper from Malvina. Malvina, I think, is on the audience. Hi, Malvina. I have read your paper, and I found 3 nice examples of bias in this paper, so I have copied them here. It's very. So let's see 3 examples that are really nice and show statistical bias in the area in the medical domain. So, the first one is that due to various barriers, vulnerable groups are likely to be significantly underrepresented in main sources of health data, such as electronic health records, right? So this means that we don't have enough data for these vulnerable people, so to train our AI algorithms. Okay? And this means that by definition from the start, these vulnerable groups are misrepresented in learning. Another example is when an algorithm that is used to distinguish between malign and non-benign moles, if we train in skin patients, it might fail to diagnose this type of moles in people with darker skin. And the third example of statistical bias is when for diseases that are more common in specific group, for example, cardiovascular diseases may underperform on women because we don't have enough data. Now, another form of bias is societal bias. And these are objectionable social structure, human biases that then can reflect it in data. Or, for example, again, an example from Ioannina, when healthcare professionals suspect immigrants that they exaggerate their health problems, and he administer incorrect doses. This is part of the medical history of the patient, okay, and this is given again as input to an algorithm. And the cause of this is not statistical bias, it's societal bias, right? And then because people design, implement, and evaluate and use these algorithms, they introduce their own societal and personal bias in the algorithm. And then there are a lot of biases. As humans, we have a lot of biases. So I will, for example, confirmation bias. Confirmation bias, I don't know if you have heard about confirmation bias. It's a very strong bias. It's our tendency to accept more easily things that are close to our own beliefs, right? And this is a very strong bias. We tend to dismiss things that are not in concordance with our own opinions. Okay, and here let's see. So there is a lot of bias, and bias can be part from the data or in the algorithm. So we commonly say garbage in, garbage out. And let me give you a few more examples. Say a survey or a poll contains bias question. This is societal bias. The people who design the poll introduce their own bias in designing their poll. If some specific population is presented in the input data, the statistical bias. If the data itself is a product of a historical process that is operated to the disadvantage of certain groups. Data social mirror. We saw an example with the beddings, right? This is a societal bias that is reflected in the data. And then we have bias in the algorithms, for example, reflecting commercial or other preferences of designers, statistical bias in data processing, and then this is called a feedback loop or bias amplification. So if an algorithm receives biased data, it produces biased data, and this biased data is then used as input to an algorithm, and this way the bias is exaggerated. Okay. For example, take ChatGPT. You train it with text. It produces data. Then this data can be biased. ChatGPT is its learning is trained with its own output, and this results in this feedback loop. Okay, so so far we have seen, we have discussed the two questions that I have set in the beginning of this talk. Question number one, can an algorithm be unfair? Question number two, what is the causes of this unfairness? Now we move to question number three, how can we mitigate unfairness? And I'm going to give you an overview of models that have been used to measure unfairness. Okay. How can we measure unfairness in the output of an algorithm? That's the first question I'm going to address. And of course, fairness is a very general term. And there are philosophical, ethical, political, judicial interpretations of fairness. And a little bit of trivia, fairness is not a Greek word. Okay. It comes from the Old English figure, I don't know how to pronounce it, meaning pleasant, attractive, which came from the Germanic Norse fagar, or fagr, for beautiful. So the very term of fairness includes beauty, right? And I don't know how we can translate fairness in Greek. Any suggestions? It's not the same as justice, but it's a different word. It's fairness, right? So it's something that's also beautiful and nice. Okay, so that's this nice word. And now, perhaps you have seen this figures like that, and let me explain the difference between equality and equity. Equality means that we treat everyone the same. And the first small figure shows that. So we have 3 people of different height, and we treat them fairly, we offer them the same box. Equity is everyone according to their own needs. So we give them boxes of different height, and now we have the same amount. Okay. So in the first, with equality, we treat everybody equal. With equity, we treat everyone according to their needs. So the output of the algorithm is the same. And finally, we can have justice. It means we don't care if the world was just, then we didn't need to do anything, right? No barriers, and this is justice. Okay. So many of the technical definitions of fairness try to capture either equality or equity. Okay. Now, how do we measure fairness? So far, fairness is considered as lack of discrimination. That is, the results of an algorithm should not be influenced by protective or sensitive attributes such as gender, religion, race. And in a very, very high level, we have 2 types of fairness: individual fairness and group fairness. Individual fairness simply says that similar individuals should be treated in a similar manner, whereas group fairness partitions individuals into groups, male, female, and ask that all groups are treated fairly. Now, the exact formalization, the exact model of individual and group fairness depends on the specific AI algorithm. Okay. For example, it's different when we have classification algorithms, when we have recommendation, ranking, clustering. Okay. So I'm going to talk mainly about classification, but there is a lot of work and very interesting problems when you try to formalize fairness for other types of AI algorithms or tasks. Okay, so individual fairness. It's very, very difficult to model individual fairness, and this is a very abstract formalization of what we do. To model individual fairness, we need to, most often we assume a distance metric, a way to capture the similarity or dissimilarity between individuals. Okay, so we define let's say we have X and 2 individuals, X and Y. We need to define a distance between X and Y to capture how similar they are. And then we ask that we need a different distance function. I've noted it D capital to capture the distance between the output of the AI algorithm on X and the output of the AI algorithm on Y. And intuitively, what we want is the distance in the output to be proportional to the distance between the actual individuals. Okay. So this is a very high level description of individual fairness, and for specific problems, you need to define these distance functions, which is very difficult, especially when you want to define distances in the input space between individuals. Now, group fairness is easier to understand. So let's assume that we have two groups, the blue and the red group. The blue group, the red group is the protected group, the minority group, and blue is the non-protected group. Let's call it the privileged group. Okay. Now, before I show you some definition of group fairness, let me make a note here. There is a lot of ongoing work and in group fairness along two issues. One is what happens when the protected attribute has continuous values. For example, the protected attribute is age. How do we define groups when we have age? What is the range of values? And then when we have more than one protected group. Okay, for example, let's say we have both race and gender. Okay, so one is that we can take it as an additive interpretation where we can prove it independently. But there are cases what called intersectional, where unfairness is a result of the synergy. For example, race or gender cannot be alone, may not be an issue, but in combination, they may cause unfairness. For example, black women. Okay. So there's this different interpretation and different dimensions here. Okay, so let's see some examples of concrete definitions in terms for group fairness in classification. Are you aware of the classification problem? How many of you know classification? Okay, so I will give a very short introduction. In the classification problem, you have individuals. Let's say that our individuals are the blue and red dots here. And what you want to do is you want to map them in some class. In binary classification, we have two classes. In this example, we have the positive class, class 1, and the negative class, class 0. And as an example, to have something to think about, say that class 1 is I get the job, class 0, I don't get the job. Okay, so we have individuals, and we want to map them in class 1. They get the job. In class 0, they don't get the job. Okay, and I will use Y for the actual output, the ground truth, meaning that I know the ground truth. I know which people should get the job. This is Y, and Y hat is the predicted output, what the algorithm says. Okay. So I have Y and Y hat. And in this example, you see the predicted output is here. These 4 individuals take the job, and this is the Y. The predicted output is 0. They don't get the job. And just to give you the intuition, we want to decide if this output is fair. Okay. In this output, for example, one red person gets the job, and the 4 red people don't get the job. Is this fair? How can we determine whether this output is fair? Okay, so that is what we are trying to capture. This is the output. When is this output fair, right? And the first approach to group fairness does the following. This means what is the probability that I get the job? The estimation is that I get the job if I am a blue person, and this is the probability, the estimated probability that I get the job if I am a red person. So we compare these probabilities. Okay. The probability to get the job if I am red, the probability to get the job if I am blue. Okay. And the most common definition is asking this probability to be 1. Okay. So I have the same probability to get the same estimated probability to get the job if I'm blue as if I'm red. And this models equity. Members of each group have the same chance of getting the favorable outcome. It is also known as demographic parity, statistical parity or the dependence, because it preserves the input ratio. The demographics of the individual receiving a favorable outcome is the same as their demographic in the underlying population. An example: if in the applicants 10% of the applicants are women, then 10% of the people that get the job are women. Okay, and this is called demographic parity. Now, there is a type of here, smaller e epsilon. Okay, this demographic parity is just an example. We can fix this ratio and say something like 20%, independently of the percentage of women in the population. We have 20% women getting the job, right? This is often called the disparate impact. Independent of how many women, we get 20 women to get the job. So 20% of the women to get the job. Okay. Okay, my note here is that, but I'm not going to get in details. Something to think about. Say you want to have the same rule when you have rankings. Okay. What we mean by rankings is, say you have the results, the Google results. Okay. So you have ranked results. In ranking, we have what is called positional bias. In Western cultures, we read from left to right, top to bottom. So the person that gets the top leftmost position is the link that the link that you're going to click on. Right? So how can we enforce this kind of fairness when we have ranking and when we have recommendations? Now, the thing with demographic parity is it ignores the actual output. In simple terms, we say that 20% of the women will get the job independent of their qualifications. They will get the job. Okay. Now, this group of there is a group of formal definitions of fairness that take into account the ground truth. Okay. In simple terms, the ground truth is the actual qualifications of the people applying for the job. Okay. So those definitions are are based on errors, and I'm not sure whether you are familiar with the confusion matrix. Are you aware of the confusion matrix? Okay, so it's easier for me to explain. So what we do is that one of the most common definitions in this is that we look at the probability of a blue person to get the job if he is qualified, right? If the ground truth is 1, get a job, you actually the predict outcome is also 1. Okay. This is called true positive rate. Okay. And in this case, you look at the true positive rates, and we ask that the true positive rates are equal. And this is also known as equal opportunity. Or, okay, so the difference between equal opportunity and statistical parity is that equal opportunity takes into account the qualifications, the ground truth. Okay. And this, in a sense, this is a statistical parity models equity, whereas equal opportunity models equality. Okay. And then there are other definitions that are based on looking at errors. For example, equalized odds, which means that we look both at both the true and false positive rates, and we ask that they're equal for both groups. Okay. And again, there are error-based fairness definitions for other types of AI tasks for recommendation. For example, we ask that the error in recommendation score of the member of each group is equal. So this kind of definitions look at the performance of the AI algorithm and ask that the algorithm performs equally well. It bounds the error for both groups. And this is a summary We talk about demographic parity. This is also called independence. We talk about error rates. It's also called separation. And there is a third type that I didn't talk about. It's a little more complicated. It's based on calibration, and it's also called sufficiency. Okay. And the third type of group fairness, of fairness definitions are what is called counterfactual fairness. And in this case, a decision is fairest towards an individual if it is the same in both the actual world and in a counterfactual world where the individual belongs to a different group. And to prove a counterfactual fairness, we use basically causal analysis. Okay, so we've been discussing question number 3, how can we mitigate fairness? And I presented you in a high level 3 different models of unfairness. Individual models based on distance, group-based models or statistical models that look at, we saw them for the classification problem, and I briefly mentioned counterfactual fairness. Right. Now let's talk a little bit about how can we mitigate unfairness. Okay, I hope you can hear me because of the noise is really loud. Okay, so it's I have a nice background noise, right? Okay. Okay. Now, how can we achieve fairness? There are 3 different approaches for achieving fairness. One is pre-processing. This type, what we do is we pre-process the data. We don't look at the algorithm, forget the algorithm, we pre-process at the data. For example, we try to debias the input data. The second type is called in-processing. Here, we change the algorithm. So the algorithm produces fair output, whatever that means, depending on the model, right? Independent of whether the input is biased or not. In-processing. Okay? And then we have post-processing, where we don't care about the algorithm, we don't care about changing the input data, only at the output, and we tweak the output, we change the output so that the output is fair. Okay, so in pre-processing data, input data, in processing the algorithm, post-processing the output data. So, what do you mean? Okay. Okay, so the question is, can we change the output? Well, then let's say an ethical condition, question, or for example, you want to enforce 20% women get the job principle. Okay, but the qualified women are not. Then you have to tweak the output to do this, right? And okay, the point here, and I have a slide on that, is the following: that you want to change the output, but you cannot do whatever you want, right? So you need to. The one requirement is fairness. The other requirement is accuracy. You want to make the minimum changes so that the output is as close as possible to the original output, right? So that's the two conditions we have when we do post-process. Okay, so just one quick note on in-processing. So one would ask, why not hide the protected attribute? Okay. Do not take into account race, gender, whatever. Okay, this is called blindness, and it doesn't work because there are proxy attributes. What are proxy attributes? Attributes that their values is correlated with the protected one. Okay. So, for example, even if we don't, you recall one of my examples. Even if we don't consider race, the history of the medical data of Black people somehow you can induce the arrays from their history, right? Another more clear example is with zip codes. Okay, so we can ignore race, but sometimes race is encoded into zip codes because there are neighborhoods where the majority is from specific race, right? So using zip code is a proxy for race. And this is called redlining, and it's not allowed in the US. Okay, so the simplest solution: do not consider the protected attribute, does not work. Okay, now there are many ways to do processing. I won't get into details. I will give you some references for all this. One is one of this is you can change the label of some objects to remove the discrimination. For example, you can change the label of the labels of some members of the protected group to the favorable category. These are called promotion candidates, and again select a member of the majority group and change also their labels. They are true labels, and this is called demotion candidates. And this is one of the approaches. There are many more. Here is a list of different ways to do pre-processing. For those that I will share my slides if you want to get into details about the different ways. Now, in processing, this is a bit technical, but I'll just to give you an idea. For in-processing, there are many different ways to do in-processing. Okay, so I will give you the high-level idea, and I will then describe this one. I don't know if you are aware of loss functions. Have you heard about loss functions? Okay, so great. So one in a very high level, one very common way to incorporate fairness inside algorithm is to modify the loss function. Okay, basically what you do is you add a factor in the loss function to capture unfairness or the requirement for fairness, right? So you train your algorithm with a loss function that has a factor that captures unfairness. This is a very high level description, but it's followed in many algorithms of this type. Here I have a different approach that introduces an intermediate level, which is called a fair representation approach. In a very high level, you have the input space, x, the output space, the classification. You introduce what's called a fair representation, an extra space, z, which is a representation of x that hides the sensitive information. And then again, you have a loss function that tries to that enforces various requirements. One is you enforce statistical parity, fairness on the z. You also want the representation to be as close as possible to x, and then you have a third term for the accuracy. Okay. There are many processing approaches. So in this very high level talk, I just wanted to show you some examples, right? And then there is post-processing. We basically somehow cover the basics of post-processing. The idea is that we have fairness and we have a measure of utility. That means we want to change the output having in mind two objectives. One is fairness. We want it to be fair. And the other is accuracy. We want it to be as close as possible to the original output. Okay, and there are different ways to formalize that. For example, you can maximize fairness subject to a constraint of utility. You can say, I want the maximum fairness, but I don't want to lose in accuracy. Or you can do it the other way. You can maximize utility, but you put a constraint on fairness. Okay, so so far we have already addressed my 3 questions, and I will repeat it once more. So question number 1: can an algorithm be unfair? Yes. Question number 2: what are the causes of unfairness? Bias. Question number 3: how to model and counterfactor fairness. We have seen 3 models and 3 types of models, and we have seen 3 types of counterfacting unfairness. And I'm reaching the end of the talk, so I'm going to give you some additional resources and a few concluding slides, concluding remarks. Okay, some additional resources. There is, okay, in terms of conferences, there are fairness papers regarding fairness in all major computer science conferences in all areas. Right? There is one conference dedicated to fairness. It's called FACT, ACM Conference on Fairness, Accountability, and Transparency, and it's a kind of interdisciplinary conference. So if you are not necessarily computer science, this is a conference that you can send papers because it's quite interdisciplinary, right? Then there is a free online book. It's very good, and I think that independently of your background, there are chapters there that you can read and learn from. So if you are interested in fairness in AI, this is a good starting point, this book. Okay, and then there are many tools. With tools, I mean software libraries that implement fairness metrics and algorithms, like the fairness metrics and I have been talking about, and the algorithms that I have not been talking about, those that I gave you an idea of. One of the most well-known is the AI Fairness 360. So if you have time, you can check it. And they also suggest if you are designing an AI algorithm, right, and you are curious whether your algorithm is fair or not, why not try AI fairness to check it, right? And it will give you another perspective on your work. Okay. And there are other tools. So I suggest AI Fairness 360, and I think FairLearn is the third one is also rather inclusive. And then TensorFlow has also some specific libraries that are called responsive AI. You can check it. Okay. Okay. So we have seen the why, what, and how of fairness in AI. I think it's I think it's a very timely and a very relevant topic. It's a fast-changing area. It's a hot topic. Many new results come out all the time. I think it's an area that with many opportunities to do important research, and also I also believe this is an area that if you work on this area, you can also have some real impact, right? So I'm really fond of this. Okay. So as I said, that I want to emphasize again, because this is, I think, is the right summer school, the right audience. This is really interdisciplinary. It's not just ethical, political, technical, social, legal, philosophical. It's all of it, right? And I think the group here, the mixture here, is the perfect mixture to address AI fairness in medicine. So we have people from the medical profession. They have the field knowledge. They know what is needed. They are the people that are going to use these algorithms. We have computer scientists that can tell us what is feasible, how can we measure it, how can we operationalize fairness, how to implement it. And we have people from law that can explain us what and how can be enforced. So it's really a matter of synergy more than working alone in a topic. If you want to have a real impact. Okay, so this is my concluding slide. I have some references. We are working on various issues on fairness. I have not put there of our own work, technical work. We work on fairness in graphs, and and things like that. But I have put references on some of the papers we have written that are more general than addressing specific research problems in fairness in AI. So thank you, and that concludes my talk.